In part 2 of this lesson, I'll show you 4 more examples on how to test for convergence in a sequence with limits. The question reads, for each of the following examples, determine whether the sequence converges or diverges. If it converges, find the limit. We'll be using the exact same theorem in part 1, and it's stated right here. We'll start with the first sequence, which is defined as a sub n is equal to 8 times arctan n. To find whether this converges or diverges, you need to know what tangent looks like, its graph. And only roughly. If you recall, the tangent graph looks like this, where you have bounds between negative pi over 2 and pi over 2, and this happens incrementally. So whatever your wave looks like, it cannot pass through these constraints. In fact, it looks like this. Now to find out what arctan looks like, you have to flip the coordinates along this wave, given that it's the inverse function. So the arctan will look like this, where these bounds are on the y-axis. This is pi over 2, and let's say that this right here is negative pi over 2. That being said, if we take the limit as n approaches infinity for our function 8 arctan, which can be written as tangent inverse of n, if we substitute a very large number into n, as you can tell, this wave will reach a maximum of pi over 2. So this right here will become pi over 2 multiplied by 8 gives us 4 pi. This means that this sequence converges, and we'll write that down in a formal way, to 4 pi. Let's move on to the next one. We're asked to find whether 6 to the power of 1 over n converges or diverges. This one's easy. If I substitute a very large number into n, I'll end up with 1 over a very large number, which is equal to 0. 6 to the power of 0 and anything to the power of 0 is equal to 1. Therefore, this one converges to 1. I've written that down for you, and it's on your screen. In question number 2, they want us to use Lhopitals Rule to evaluate the limit. Lhopitals Rule tells us that we can take the derivative of the numerator and the denominator and then take its limit to find out the limit. So let's go ahead and do that. First, I'll set a sub n equal to f at x. So I have f at x is equal to ln x over x to the power of 7. I'll take the derivative of ln x, and it's 1 over x, and I'll take the limit of x to the power of 7, which is 7x to the power of 6. Let's take the limit of the numerator. Placing a very large number into here makes this go to 0, and placing a very large number to there makes it infinity. 0 over infinity is equal to 0. Therefore, a sub n, our sequence, converges to 0. In question number 3, they expect us to use the squeeze theorem to evaluate the limit. The squeeze theorem is an interesting concept, and you can use this to take the limit of certain functions. I do have a video dedicated to the squeeze theorem. And I'll try to squeeze the function between two bounds. So I'll say that cosine n is less than or equal to negative 1 and 1. And technically it is, given that cosine is a periodic function. Now I will divide each of these terms by n to the power of 2, n to the power of 2, n to the power of 2, n to the power of 2. I'll add 5 to each part, so I have negative 1 over n to the power of 2 plus 5 is less than or equal to cosine n over 2 plus 5, and 1 over n over 2 plus 5. I'll take the limit of this part. If n goes to infinity here, this becomes a 0, this term, so we have 5. If I take the limit as n approaches infinity for here, I'll also end up with 5. Therefore, by the squeeze theorem, this part, its limit, is equal to 5. And we can write this down as a sub n converges. And there you have it. That is how to test for convergence in a sequence with limits.